Since its formation, our planet has undergone constant transformation. Stupendous collisions have created continents. Colossal forces have raised up ocean floors, forming dramatic mountain ranges. These movements on the Earth's surface can still be seen today, as evidenced by volcanic eruptions, earthquakes, and tsunamis. Tectonics sculpt our landscapes, alter the climate, change the course of oceans, and can even influence the living world. For millions of years, fragments of the Earth's crust have come together and broken apart, resulting in volatile upheavals. Even today, the continent carries scars of its tumultuous past. From smoky craters to craggy mountaintops, specialists track these hidden clues. In their hands, every rock, every fossil becomes a word on the page in the story of North America. An exceptional testimony to the never-ending voyage of the continents. At its birth, 4.6 billion years ago, the Earth is a gigantic ball of lava. Then it cools, and rocky plates aggregate, forming the first fragments of the Earth's crust. Thus begins the first chapter of the history of the North American continent. In Montreal, located in eastern Canada, it so happens there's a researcher who studies these vestiges of our planet's infancy. Professor Don Francis works in the Department of Earth and Planetary Sciences at the prestigious McGill University. Every day, he rides his bike across Montreal's historic city center to his laboratory. This area is ideal for geologists because 90% of the province of Quebec is covered by what's called a craton, a fragment of the Earth's crust which has remained unchanged for billions of years. The rocks that crop out here are not the oldest. But for the scientist, each one will likely reveal an element of North America's story nonetheless.
So all these rocks are much younger than the rocks of the craton, which normally are 2.7, and our team have discovered an area in the craton where the rocks are as old as 4.3 billion years old. This is a very old age, and the rocks there tell us a lot of interesting things about that time. For example, we know that because there are pillow lavas there, that there was an ocean. This was at a time when the moon was being bombarded by very large meteorites. All the big craters you see on the moon were produced during this time. And in fact, it must have been happening on the Earth as well. So you have a marine environment where there are hot springs and there are big meteorites falling out of the sky. So it's a very unusual environment.
Don Francis and his colleagues recently discovered these rocks dating back 4.3 billion years in northern Quebec. The announcement caused a sensation in the scientific community. These rocks are, in effect, the oldest specimens ever discovered. The study of their structure gives an unprecedented view of the environment that reigned on primitive Earth. But the geologists must still confirm the rock's age in a definitive manner. To do this, they look for traces of a particular mineral inside the granite, zircon. This mineral is known to be exceptionally stable and to contain infinitesimal quantities of uranium, which over time transform into lead. Thus, by calculating the proportions of lead and uranium in the zircon crystals, the exact age of the rock can be determined. Cut in very fine slices, the samples reveal their inner structure under the microscope's lens.
Here's one of these garnets. They're black with the filter in, but when you take the filter out, they're clear. And that's the way you identify garnet. Up until recently, 3.8 were the oldest rocks. The result of that is a lot of people are now going back to 3.8 areas, of which there are not very many. You could probably count them on two hands, maybe less. But they've been going back into these areas, trying to see whether they can find the same anomaly that we found, and to see whether there are, in fact, more than one occurrence of very old rocks.
Every day, Don teaches his students the history of the Canadian Craton. Other tests are still necessary to assure that the oldest of the rocks are indeed 4.3 billion years of age.
The field trip is going to be to the Mont Region Hill.
But if the results are confirmed, a new chapter will be added to the class syllabus, that of the birth of the North American continent's very first landmass. Later, fragments of the Earth's crust spread across the surface of the globe, migrating and combining with one another. When they collided, mountains were created. When they broke apart, oceans and seas were hollowed out. Then water and rain eroded their surface over millions of years. Traces of these ancient events are still visible today, notably on the Colorado Plateau in the heart of Monument Valley. Here, successive layers of strata testify to the never-ending evolution of the relief over millions of years. But the tectonic plates are always in motion. And 500 million years ago, the continental land masses in the northern hemisphere began to draw closer. Little by little, they began to collide with Africa. And about 100 million years later, a vast supercontinent was formed, the Pangea. Today, the landscapes tell the story of Pangea's birth, a major event in the history of North America. Southeastern Canada, in the province of Nova Scotia, the city of Passborough is located near the Appalachians. A vast mountain range born when America and Africa collided. Paul Olson, a geologist and biologist at Columbia University in New York, knows the area by heart. He's roamed these coasts for many years in search of new clues to Pangea's history.
This is Nova Scotia in eastern Canada. 300 million years ago, on this spot, North America and Africa collided, producing Pangea, the last of the great supercontinents. This is really the center of the action. Let me show you with a drawing. Here's North America, and it's heading this way. And here comes Africa, and it's being shoved below North America. And when they finally collide, they produce an enormous mountain range, the Appalachians.
Sprung from the Earth 270 million years ago, today the Appalachians spread over more than 3,000 kilometers. A veritable open-air geological archive, it's the proof that long ago America and Africa formed one and the same territory.
When the North American and African plates collided, they did so with tremendous force, so much so that they shoved the rocks up from their original flat-lying positions into these twisted and contorted forms that you can see here, barely recognizable from the way they were when they were formed. And you can find exactly the same kind of rocks in Africa today. So what actually happened? At about 50 million years later, the North American and African plates began to collapse. And as they collapsed, Africa began to pull away from North America, and the crust began to stretch and sink, forming a giant rift basin, when finally the Atlantic Ocean formed about 200 million years ago.
The opening of the Atlantic Ocean marks the end of Pangea. But this fracturing makes for a bumpy ride. As the continents break apart, the Earth itself fissures in all quarters. In the interstices, astronomical quantities of magma rise from the depths of the mantle. Massive successive volcanic eruptions continue for more than 600,000 years.
Now that rock is really interesting. On this side, you see red sediments deposited by streams and rivers. On this side, you have a completely different kind of rock. It's called basalt. It's basically hardened lava. It's 201.6 million years old. And it's vivid evidence of the formation of the Atlantic Ocean, right here. If you look carefully, you can see little white dots. Those are minerals that filled in holes that were originally filled with gases. And those gases caused a mass extinction at exactly the time of the eruptions of these lavas. One that shaped the future of life on Earth, and in fact allowed our ancestors very long ago to survive and fill the world. Animals and plants were quite different in different places, and there was a tremendous amount of diversity on the land. There were crocodile relatives that were dominant in the landscape over all of Pangea. However, when North America and Africa began to split apart, and the lava erupted in that enormous area, the gases that were produced by that eruption caused climate changes that killed off almost all of the crocodile relatives, leaving ecological space open for the dinosaurs to occupy. And after that is when dinosaurs actually took over the Earth, and we begin the real part of the age of dinosaurs.
200 million years ago, the tectonic plates resulted in a massive extinction of species.
These are interesting.
In total, half of the Earth's biological diversity disappeared, giving the dinosaurs free rein. Thus began their unrivaled dynasty on the planet. Along the banks of Nova Scotia, a few of these reptiles' fossil prints are still visible, the last remnants of their former domination. But much further inland to the west, these Cretaceous giants left other evidence of their passage. In the Canadian province of Alberta, the city of Drumheller houses the Royal Tyrrell Museum, the largest in the world dedicated to dinosaurs. Gathered here are the skeletons of hundreds of specimens representing more than 35 different species. François Thérien is a paleontologist and geologist. His specialty, the study of the environment and behavior of dinosaurs during the Cretaceous period.
So we're here in the storage room. It's here that plaster jackets containing the fossils are stored until they can be prepared. As you can see, there are a great many fossils. The oldest date back to 1962. and we'll probably never be able to prepare all of them. There are so many specimens. It is always a priority. We always prepare the nicest specimens before the others.
Hi, Donna. How are you?
Hello, I'm good. How are you?
Good, good. What you working on?
I'm working on a gar block.
Oh.
3D gar. Very rare. So far, I've found about 20 of them in here.
Cool. Well, I was coming to ask you, do you want to go to the field, go to the Tolman Ceratopsian dig site?
Sure.
Cool. Okay, well, I'll have a few things to do, and then I'll just meet you at the site then.
Cool.
Cool. See you there.
The Alberta region is François Thérien's main excavation zone. The great majority of fossils exhibited in the museum come from an area called the Badlands. This valley, with its almost lunar scenery, draws a long scar across the Canadian West. It formed 100 million years ago. At that time, the face of North America was vastly different from these spectacular landscapes.
About 180 million years ago, at the end of the Jurassic period, a subduction zone developed on the west coast of the North American continent. Because the crust fragments rose and pressed down on the North American, the continent started to sag, forming a huge depression in the middle of North America. Over millions of years, the marine level fluctuated in such a way that the ocean invaded the center of the North American continent, developing a great inside sea that connected the Arctic Ocean to the Gulf of Mexico. Great coastal plains rose up around this inside sea. These coastal zones were inhabited by the dinosaurs.
Buried under the sediment, the skeletons of reptiles have traversed time and reappear today in a perfectly preserved state.
Hey guys. How's it going? Good, good. Anything new? A skull or something?
Since dinosaurs only lived between 230 and 66 million years, we have to find the rocks that were deposited here during that period. So south of Alberta is the best place on Earth because it meets these criteria. There are rocky outcroppings that formed around 80 to 66 million years ago, deposited in the rivers and lakes, and we also have the advantage of a very arid climate, which limits plant growth. There are no big forests to cover the outcroppings, so there are a lot of rocky outcroppings, which means we can walk about the typical Badlands landscapes and discover other dinosaurs.
François and his colleagues delicately probe the soil, looking for the tiniest fragments of fossilized bone. And like every year, the prospects look good.
We see here, it's a bone poking out of the rock. It's the backbone of a horned dinosaur, a ceratopsia. So in fact, we can say that tectonics aren't only responsible for forming the Great Plains of the North American continent, but tectonics are also responsible for providing ideal conservation conditions for all the dinosaur bones we find here. As the rocks rose and the Earth's crust sagged, there were a lot of rivers running towards this inside sea. These rivers overflowed the plains with alluvium and buried all the animals here. And it's thanks to this tectonic phenomenon that we can admire dinosaur bones in museums all over the world.
Tirelessly, each year the researchers continue to unearth new bones. These fossils make it possible to deepen our knowledge about dinosaurs, but also of the history of the Great Plains, the swath of terrain born in the heart of North America more than 100 million years ago. But further west, the age of dinosaurs is marked by another major geological phenomenon. The continent drifts slowly, colliding with fragments of the continental crust dispersed across the ocean surface. These tiny islets of land successively graft themselves to the North American plate, which grows little by little. This is how the four most westerly states on the continent, Nevada, Oregon, California, and Washington, were formed. Alan Glasner, geologist at the University of California, studies the history of these collisions that gave North America its final shape. He carries out his research in the heart of Yosemite National Park. With its mountains, lakes, and waterfalls that hurtle down the slopes, it's one of the most beautiful parks in all of the United States. The result of the encounter between North America and the future Western states. The collisions caused a folding of the rock and provoked violent volcanic eruptions. Magma rose from the depths, and as it cooled, formed these gigantic granite domes.
If you looked at Western North America from space before Pangea broke up, it would have looked quite different. Much of today's Nevada, Oregon, Washington, California would have been underwater. But as subduction started, as North America moved westward, then suddenly the continent started to grow because you started adding things like the granite we're standing on. And if you look at it carefully, you can see lots of detail in it that shows you how different pockets of magma came up and cooled and crystallized to form this body here. And one of the most obvious examples of that are these late dikes that came in. As the magma cools, as it gets almost 100% crystallized, it cracks, and the very last liquid gets sucked into those cracks to form these beautiful dikes that show up so well on this glaciated surface.
These veins of rock, which scientists call dikes, are proof of intensive volcanic activity in the past.
So on the map, we've mapped out all these different pulses. Some of them are dark colored, some are very light colored stripes, and they allow us to work out a sequence of injections of magma into this area.
Magma from the Earth's depths has thus infiltrated fissures in the rock to reach the surface. There was a time in history when Yosemite National Park, like the rest of the American West, was in fact located off the coast, in the middle of the Pacific Ocean. But when pieces of the Earth's crust collided, they finished by melding into a single continent. Around these collisions, the Earth gave rise to California's highest mountain range, the Sierra Nevadas, which stretch more than 700 kilometers from north to south. In the field, Alan Glasner constantly analyzes clues to these past events to recover the details of the region's geological history. Today, he is joined by one of his students, at the foot of the park's most famous monolith, El Capitan. Here, the granite cliff rises more than a kilometer high.
Roger, how's it going?
Going well. Yeah, check this out, Alan. Here's a piece of that apatite. What's the black? Biotite?
Yeah, all I can identify is biotite. That's a pretty rock.
Yeah.
We should definitely get a sample to analyze if it isn't in your database already.
Yeah, I don't have it from specifically here yet, so yeah, let's get one. I think one of the coolest pieces about the geology of El Capitan is that where we are right here at the base of El Cap was 10 kilometers below the Earth's surface 104 million years ago, which is the same time as dinosaurs were roaming the Earth. So 10 kilometers above where we are now, there were dinosaurs walking around, which is just one of the coolest things.
And there were big volcanoes going off at the same time, so those dinosaurs had a lot to worry about.
Today, the Sierra Nevada's highest summit reaches an altitude of 4,400 meters. But this height pales in comparison to the colossal mountain that stood here in the past. Because over millions of years, water, wind, and ice have worn down the rock. From the summit of Half Dome, Alan can contemplate the effects of this slow erosion. The Sierra Nevadas are now composed of a series of valleys and mountains with rounded peaks.
When the Sierra Nevada formed, say 90 million years, and we're sitting here, you'd be about 10 kilometers down in the crust. There would be a very tall chain of volcanoes above you, and there would be a subduction zone being subducted about the normal angle of the plate was going down. It may be 45 degrees. I'll make a sketch to illustrate that better. When the subducted plate gets to a depth of about 100 kilometers, then chemical reactions occur that produce magma. And so this magma rises, being less dense, gets to the surface, it piles up and erupts, forms volcanoes and lava flows. It erupts volcanic ash, and some of that magma gets trapped in the crust at depths of, well, let's say 10 to 20 kilometers. And when it cools and hardens, it forms granite. And that's what we're standing in here. Erosion has taken off the upper layers of the crust, and we're down within this magma factory.
The Sierra Nevadas, with its sumptuous landscapes, is one of the places that best demonstrates the constant evolution of the continents. It was here, 100 million years ago, that North America extended westward to take on its current form. But during the same period, a different phenomenon was taking place a bit farther east. Another mountain range was also rising from the Earth, the Rockies. This massif stretches for more than 4,800 kilometers from New Mexico all the way to northern British Columbia. The Rocky Mountains formed during the same period as the Sierra Nevadas, but for a long time, they mystified geologists the world over. Generally, mountain ranges are born at the edges of colliding plates. How then do we explain the presence of these peaks nearly 1,000 kilometers inland? Today, a hypothesis is at last taking shape. About 80 million years ago, a plate slid under the North American continent, but instead of dropping down at a 45-degree angle, as is usually the case, it wove its way in much closer to the surface. As a result, the rock didn't reach a sufficient depth to be melted by the heat. So the plate continued its journey, and jamming against the Earth's crust in its path gave rise to the Rocky Mountains. Today, not every detail of this event has been perfectly elucidated. But in all likelihood, the origin of the Rockies is a geological anomaly, a willful plate that suddenly refused to submerge. Backed up against the Rocky Mountains, another region was victim to the Earth's fitful rage for thousands of years. Yellowstone National Park, located in the state of Wyoming. Henry Heelsler is the park's geologist. Every day he roams this immense natural reserve. His mission, watch over the monster that sleeps just beneath the surface, a supervolcano of unimaginable strength. For years, specialists have tried to understand the origin of this supervolcano. They finally discovered that Yellowstone Park is situated on what is called a hotspot. These are zones where under the surface, the base temperature is unusually high. Thus, enormous quantities of magma rise from the depths and accumulate in a pocket several hundred kilometers under the ground called a plume. When the magma is expelled, it pierces the Earth's crust and a volcano appears. But when the tectonic plate slowly floats above it, the hotspot doesn't move. It thus imprints its mark at regular intervals along the Earth's surface. In the last 2 billion years, the Yellowstone region was the site of 3 major eruptions. The last one dates back 642,000 years. Accumulated beneath the Earth's crust, the lava burst from its chamber and projected thousands of tons of molten rock, volcanic ash, and sulfurous gases into the air.
When material is forcefully erupted, not as a big blast, but basically vented through all the fissures and cracks that were forming in the Earth, it forms a caldera, which is a subsidence feature, and behind me you can see the evidence for that. Basically, the caldera starts almost exactly where I'm standing and then goes 72 kilometers directly behind me, where it's covered by more recent lava flows.
In the heart of the national park, the Yellowstone caldera forms a gigantic basin 72 kilometers long by 56 kilometers wide. It's all that remains of this colossal explosion, one of the most devastating in the history of the Earth. But today, the supervolcano is far from extinct. The Earth here rumbles non-stop. Geysers, gas, and vapors, as well as other heat sources, punctuate the landscape, evidence of the intense activity that reigns beneath the surface. The volcano is simply dozing, and it's potentially one of the most destructive on the planet.
The super eruptions of Yellowstone, catastrophic for hundreds of kilometers around what currently is Yellowstone National Park. There would be no life left because of the force of the eruptions, the pyroclastic, the hot rock flows that come out tens of kilometers, the resulting ash clouds, the volcanic ash and volcanic gases that would be ejected high into the atmosphere and basically circle the entire globe would cause a volcanic winter to cover the entire world.
For many years, Yellowstone's supervolcano has been under close observation. The control center is located about 500 kilometers from there at the University of Utah in Salt Lake City. Jamie Farrell is a geologist. Every day his task is to analyze the volcano's slightest flutter, thanks to a network of sensors that measures deformations of the ground in real time. Recently, he also recreated the monster's history and constructed a model of the vast magma chamber that feeds it.
So this is just a visualization tool that we use to kind of show the data that we record in Yellowstone. If you turn off the topography and we want to put on the earthquakes that we've recorded in Yellowstone as these red dots, what you can do here, you can zoom around and look underneath the ground and look at the patterns of earthquakes that have occurred from 1973 to the present. And again, there's roughly about 46,000 earthquakes here. If you want to look at a little bit of the bigger picture, we can turn on the Yellowstone plume, and that's this orangish yellowish feature here. This is basically the Yellowstone hotspot. This is the feature that's providing all the heat and energy coming up from the mantle to feed the Yellowstone volcanoes. So you can see here it comes down into the mantle. So the Yellowstone hotspot manifests itself on the surface about 16 or 17 million years ago down in this area down here in the Nevada, Oregon. So this is kind of the track of the Yellowstone hotspot as the North American plate has moved over it. The western U.S. is stretching. We have an area called the Basin and Range where the crust is being thinned and stretched. The reason why the Yellowstone hotspot is here is because of that thinning, and that may have provided a path for the hotspot to make it to the surface.
Some 3,000 low-magnitude tremors shake the Yellowstone region every year. The earth trembles, the ground is deformed, the composition of the gases evolves. But in the eyes of specialists, there is, for the moment, no proof of an imminent eruption.
Change is the normal situation at Yellowstone with earthquakes, with ground deformation, with the geothermal system, with the gases. So roughly, the probability of another catastrophic eruption is very poorly understood because we've only had 3 in the past 2 million years, but it's about the same as a large asteroid hitting the Earth and destroying it. So if you're concerned about a large asteroid hitting the Earth, then maybe you should be concerned about Yellowstone having a catastrophic eruption. The future of this volcano eventually is to become very, very cold and inactive. It will probably end with outpouring of basalts. The ground elevation will go down because it will no longer be very hot, so we'll have a very, very different looking terrain sometime into the future. It may be millions of years into the future. So the more interesting question for me is, will humanity even be around when Yellowstone changes a lot?
One day, the supervolcano will thus disappear. Until then, the volcanic gases of this hugely powerful monster will continue to dance above the staggering beauty of these lands. But today, another large-scale phenomenon is in progress. An immense scar rips through the western region of North America. Baptized the San Andreas Fault, it runs for 1,300 kilometers through California. In this area, the Pacific Plate climbs northeast, while the North American Plate descends in the opposite direction. The result? These two fragments of the Earth's crust slide against one another, making the ground tremble at regular intervals. On the banks of the San Francisco Bay, specialists from the University of California keep careful watch over the San Andreas Fault 7 days a week, 24 hours a day. Everyone here is used to the regular tremors produced by the Earth's movements. The fault line is part of everyday life for Californians. On the campus, geologist Roland Bergman teaches about the history of geology, but also of its future. Because inexorably, California is breaking off from the continent at a rate of 5 centimeters a year. In a million years, it will have become an island.
The San Andreas Fault was born about 25 million years ago. Before that time, California was a place where subduction occurred. So the San Andreas Fault is a strike-slip fault. That means that motions of blocks or plates adjacent to the fault are parallel to the fault and horizontal in a strike-slip motion, rather than one plate moving on top of the other, as we might see in a subduction zone. And if we have the San Andreas Fault continue with its motion, and there's no reason to believe that it would stop, in another 9 million years, we should be seeing the Los Angeles Basin offshore here and ruining our views.
A squeaky valve between 2 plates of the Earth's crust, the San Andreas Fault gave birth to a complex system of fissures. Several secondary fault lines have appeared and now run across the entire region. Among them, the Hayward Fault, which runs to the east, is particularly worrisome to seismologists. Aurélie Guillem is a postdoctoral candidate from France at the University of California at Berkeley. In the field, she's on the lookout for possible signs of movement along the Hayward Fault.
So here we are in the city of Hayward, which has the same name as the Hayward Fault. It was here that the 1868 earthquake took place. In addition to powerful earthquakes of a magnitude of about 7 that occur along this fault, the fault also causes slow slipping. We can observe this slow slipping on the sidewalks, like here, but also by the cracks along the streets. This sidewalk wasn't made like this. It was built straight, but since then has been deformed by the fault zone that runs through here. We can clearly see the movement in the relationship between these 2 blocks. This movement corresponds to the movement of the Hayward Fault, which has a right lateral strike slip, so the block propagates to the south in relation to this block here, which propagates to the north.
The plates thus slide slowly against one another. But sometimes the accumulated energy suddenly cracks the fault. It ruptures, provoking an earthquake.
We're at the Memorial Stadium on the Berkeley campus. This stadium was built in 1923, after the 1868 quake hit along the Hayward Fault. It measured 6.8 on the Richter scale. This stadium was built after that, and it has some deformation that can be seen on the top of the stadium here, where in fact the Hayward Fault cuts the stadium in 2. So it's been affected over time, even since the structure was built. Deformation is about 40 centimeters, and it proves that the Hayward Fault slides continuously about 0.5 centimeters per year. It's a relatively new structure, but we can clearly see a large deformation with the naked eye.
April 18, 1906, another earthquake registering 8.2 on the Richter scale hit the city of San Francisco. There were 3,000 victims, and it transformed the city into a vast field of ruins. This same phenomenon took place on October 17, 1989. 63 people died. Nearly 4,000 others were wounded, and material damage reached almost $6 billion. Today, what everyone fears is the big one, the megathrust earthquake that's supposed to hit California in the next 30 years. For Richard Allen, director of UC Berkeley's Seismological Laboratory, residents must definitely prepare for this disaster scenario.
So here we're on the UC Berkeley campus, and the Hayward Fault actually goes across the Berkeley campus. So if we have an earthquake on that fault, then we expect fairly significant damage in this area. Most of the buildings on campus here have been retrofit so that they should not collapse during an earthquake. However, many may be seriously damaged, and we won't be able to use them following the event. So while we can't predict the exact time at which an earthquake is going to occur, we know that we're going to have big earthquakes in this region over the next few decades. In fact, it's about a 2 in 3 chance of a major damaging earthquake in the Bay Area in the next 30 years. So that's how we can then get ready for these earthquakes, by building buildings. But the other thing that we can do is we can use the very beginnings of an earthquake, the P waves that radiate from a fault, to say something about the shaking that's coming and provide a few seconds warning to people before they feel the shaking.
Will the famous Golden Gate Bridge stand up to the big one when it hits? One thing is certain, the population must prepare itself for the next tragedy. Aurélie Guillaume studied the possible consequences of a megaquake in the San Francisco Bay Area. And it's from this promontory overlooking the bay that the amplitude of potential damage is most visible.
From here, we can get an overview of the Hayward Fault. So behind the hill is Berkeley with the Memorial Stadium, in front of us is San Francisco, and right there is Oakland. During a future quake, the Hayward Fault will break at this spot here with serious consequences. Below us, there's a big highway network. The Hayward Fault will cut the highway in two. This region is also very populated. And facing us, there's a gas factory right next to the fault. We imagine there'll be problems with electricity distribution in the weeks following a future quake. Something else that can't be seen here are water pipelines in that area, running east to west and thus crossing the fault line.
During the 1906 earthquake, broken water mains prevented firemen from putting out dozens of fires that ravaged the city.
If the water lines here are blocked or shut down, as well as the highways, and the electricity is out, we are looking at a pretty big natural disaster in this highly populated region.
Every day, experts are on the lookout for the slightest tremor, ready to sound the alert in the case of an imminent quake. But until then, San Francisco keeps its cool. As if the all-powerful tectonic forces couldn't mar one of the most beautiful cities in the world. North America as we know it today represents only an ephemeral stage in the planet's history. In the future, the Earth's terrible fits will continue to mold its landscape. Earthquakes and volcanic eruptions threaten one day to wreak long-lasting consequences on the entirety of the living world. And in several million years, the continent will be ripped in two. California will detach and drift at length through the Pacific Ocean. The colossal forces of the tectonic plates have not yet finished sculpting the surface of the North American continent.